We're going to look at the final three questions on Unit 5 Progress Check Part B. Number 10, the graph of f prime, the derivative of the continuous function f, is shown above on the interval -8 to 7. The graph of f prime has horizontal tangent lines at x equals -6, at x equals -3, at x equals 2, and at x equals 6.3. Vertical tangent line at x equals -4. All right, on which the following intervals is the graph of f both decreasing and concave up? Well, we have f prime, and we learned if f prime is decreasing, that means this f, that tells us about f. Oh, sorry. F is decreasing. We know that the derivative is negative, which is less than 0, so that's negative. So we want to know when the derivative is less than 0. So it's less than 0 here, except that -6, it is 0, so we might have to take that into account, and it's less than 0 over here. So it's decreasing when it's below the x-axis. Concave up, we learned, is when the derivative is increasing. So we want below 0, but increasing. So below 0, but increasing. So let's highlight this in yellow. So below 0 and increasing is here. Below 0 and increasing is here. Below 0 and increasing is right here. So that is from -8 to -6, from -3 to 0, and from, I think they said this was 6.3 to 7, which is D. So again, that was basically below the x-axis. That was the decreasing part, and that was the decreasing part here. And then when it was increasing, so number 11, the function f is continuous. So it's continuous on the interval 0 to 9, and it's twice differentiable everywhere except for x equals 6. So you see some DNEs there. Where the derivative does not exist, information about the first and second derivative of f for some values of x in the interval 0 to 9 are given in the table above, which the following statements could be false. All right, so it could be false. So we need to go through here and find out which one is false. So we'll just mark off ones that are true, and when we come to something that's false, then that's our answer. So the function f has a relative maximum at x equals 2, so we're going to come look at x equals 2. X equals 2, the derivative is 0, which means there's a critical number there. The second derivative is negative, which means it's concave down. So concave down, which means there would be a maximum at x equals 2. A is true. The graph of f has a point of inflection at x equals 4. So let's look at x equals 4. First derivative is 0, which means there's a critical number. Second derivative is 0, which means we can't use the second derivative test, which means we need to look to the left and to the right of 4 at their slopes. So the slope, let's come down here. So at 4, we know we have a horizontal tangent line of 0. It says the slope to the left is negative. The slope to the right is also negative. And so we see that has to be a point of inflection. So B is true. Next one, the function f has a relative minimum at x equals 6. All right, so that's a D and E. So critical numbers are also when the derivative doesn't exist. So we can look to the left at 6. Let's just come over here. We'll put 6 here. Something's happening at 6. To the left is negative. To the right is positive. It is continuous, so that is another minimum, which it needs to be D, I suppose. Let's go ahead and check that. D, the graph has a point of inflection at x equals 8. X equals 8. Derivative is 0. So derivative is 0. The second derivative is 0, so we need to look to the left and right of it. Well, we know to the left of it, the derivative, sorry, not that one. We want to look at the first derivative. So the derivative is positive, but we don't know what's happening after 8. So we don't know if that's a point of inflection. It could just come back down, and it could be a minimum. So D is the correct answer there. That one could be false. Could be true, but also could be false. And number 12. All right, the graph of f prime, the derivative of a continuous function, f is shown above on the interval -2 to 16. Which of the following statements is true about f on the interval -2 to 16? And it looks like, as we look at these answers, we're looking for relative extrema and points of inflection. So this is our first derivative. And so we know there's critical numbers when the derivative is 0 or undefined. So let's first look at critical numbers here. Critical number at 0, at 1, because it's undefined there. So critical number at 0 because it's 0. Critical number at 1 because it's undefined. Critical number at 4 because it's hit 0. Critical number at whatever this is, I guess about 9. We'll say 10. There's a critical number because the derivative's undefined, or first derivative is undefined. And at 15. All right, so we have at least 5 things, maybe more, but at least 5. So at 0, the derivative is 0, and the slope goes from negative to positive. So a slope going from negative to positive means that's a maximum. So on the original graph, it would have a negative slope and then a positive slope. So max. All right, so here we're looking at 1. Well, let's stick with the zeros here. At 4, we are going to have a derivative that's 0, but the slope is the slope is positive coming into it and positive coming out. So that's a point of inflection. At 15, it's 0, and its slope is negative coming into it and positive coming out of it. So a negative slope to a positive, that is a max again, which is, they're not actually asking about minimums and maxims, they're just asking about extremas. All right, so we have those. All right. The other ones, so our slope is, so at 1, when the derivative is undefined, we see our slope is positive and our slope is still positive. So there's a critical point there. Slope is positive, so that's a point of inflection. At 9 here, actually I put 9 at a maximum, so let's hold off on that. That's not what we were talking about to start with. I apologize. At At 10, the slope is undefined, and the slope goes from a positive, it was above the x-axis, and now the derivative is negative. So if the derivative is undefined and goes from a positive to a negative, that's a minimum there. All right, so we have, right now, we have 2 points of inflection and 3 extrema. However, we do need to keep looking. We have to be careful. This maximum point and this minimum point do give us something because our slope is increasing. So if we remember about the first derivative, increasing means it's concave up, and then it switches to the first derivative, decreasing, which is concave down. And so when something switches from concave up to concave down, it's a point of inflection. So whenever you have an increasing changing to a decreasing, there is another point of inflection. And here's a decreasing changing to an increasing. So this is a point of inflection. And so we actually have 3 extreme values, a max, a min, and a max. So 3 extreme values and 1, 2, 3, 4 points of inflection. So that is C3, a relative extrema, and the graph has 4 points of inflection.